Okay, good morning, everybody. I will just write Lagrangian, which I wrote yesterday to remind you what I was talking about. Okay, so this is Lagrangian in 1 plus 1 dimensions. This left and right field in 2 dimensions. D left is d mu minus a mu. D right is the same with the plus sign, and d for the scalar is with the minus sign. So yesterday there was a discussion what kind of gamma matrices one should choose. So here is the correct. Yesterday it was not correct. Okay, so the correct choice of gamma matrices is like this, and gamma 5 is gamma 0, gamma 1, 1, 0, 0, minus 1. Okay. And so this theory is a toy model which shares with the standard model many features. So one of them is non-trivial topology, complicated vacuum structure, and anomalous fermion number non-conservation. So all 3 things which we have in the standard model are present here. So the first thing I'm going to start is a discussion of complicated vacuum structure. Okay, so we imagine that the potential for the scalar field has the form lambda over 4 phi modulus square minus v square minus v square. So it has the same form as the Higgs potential in the standard model. On the classical level, the minimum of the potential energy is given by V times some phase. Okay, and we would say, okay, so that's it. Okay, you know very well what happened to this theory. We would say that the theory is in the Higgs phase. The vector field A mu gets some mass, like W and Z boson gets the mass in the standard model, and that's all. Okay, in fact, the story is somewhat more complicated, and this can be seen as follows. As I will be talking about topology, topology is best understood when the space is compact. Okay. So instead of considering, so here we have 1 plus 1, 1 is time, 1 is space. Time will go from minus infinity to plus infinity, but the space will be compact and will be associated with a circle of length L. And then eventually L can descend to infinity if you want to consider the infinite space. So this theory is a gauge theory, and so it's invariant with respect to gauge transformations. And what these gauge transformations are doing, you multiply phi field to exponential I alpha phi, where alpha is an arbitrary function of x, and you change field A by A mu minus d mu alpha x. Okay? And now looking at different possibilities of alpha x, we can realize that there are different classes of this function alpha x. So what these classes are? So the first class is the functions alpha x, which are periodic. Okay, so these are continuous functions on this circle. They are defined for x going from 0 to L. The point 0 and L I identify, and so these functions are just continuous functions which depend on L. In fact, there are also other gauge transformations which are completely admissible, and in which these functions alpha x are not periodic, but they have 2 pi n jumps at one particular point. So alpha x plus epsilon, x0 minus alpha, x0 minus epsilon. And here we put, oops, I was instructed not to write below this point. So here we have limit epsilon going to 0. So we consider this difference here. And this difference, if it's equal to 2 pi n, this is still a legitimate transformation. And looking at this formula, you see that it's completely continuous. Okay, so if you apply transformation with a 2 pi n jump to the scalar field, if it was a continuous function, it will continue to be a continuous function. Okay, and this type of transformations are called large gauge transformations, and they have a certain topology. So what kind of topology these transformations have? They match this circle on a non-trivial way on U1 group. Okay, I will write a possible transformation just explicitly. So consider alpha x, which is equal to pi I over L times x. Okay, so it has the form. Here we have 0. Here is alpha. And here is this jump. Okay? So if we apply this transformation to the scalar field, we will get phi is equal to exponential 2 pi I over L x. Well, here I put this number n times vacuum expectation value. And our gauge field, it will be just a constant. So E mu is equal to, it should be 1 over E here, where E is the charge. So we have 1 over E, 2 pi n over L. N is the integer number. Okay? So now what do we do in gauge theories? In gauge theories, you know that this type of configuration and that type of configuration are equivalent. And so this is the principle of gauge invariance. So this configuration and that configuration, it leads to the same physics. What we do in gauge theories, we remove this gauge arbitrariness, or by fixing a gauge, or by just declaring that these configurations are equivalent to each other. Okay? But this should be done in a minimal way, and it's done in the following way, that the configurations for each alpha x is periodic are declared to be physically equivalent, whereas the configurations which correspond to different topology are different physical configurations. Okay, so that's a very, very important point. So this theory contains an infinite number of vacua parameterized by integer number n is equal to 1, 2, 3, etc. So in classical field theory, these different vacua, which are represented here, they live infinite amount of time. Okay? Now, since we have quantum theory, these different vacua can be connected with each other, by different quantum transitions. And the state which survives in quantum field theory is a famous theta vacuum state. So what you do is the following. So let me denote this by n. Okay? So n is some integer, and this is this type of classical configuration. So you organize a configuration theta, which is equal to sum and equal to minus infinity plus infinity. And here you have I n theta times state n. So that's a very interesting state. This is a coherent mixture of different n state, which obeys the following property. If you act on this state by a large gauge transformation, okay, a large gauge transformation is the transformation with this type of gauge function, then this theta state is not coming to itself, but it's multiplied by I n theta. Okay, and it is this non-trivial structure which is responsible for appearance theta angle in QCD, for theta angle in this theory, etc., etc. Okay. This will not be a topic of my discussion here, because I will be interested in different things, in sphalerons and fermion number non-conservation, etc., etc. But what is important here is that you have to realize that our theory here has a set of different vector, which all have the same energy at the classical level. Energy is equal to 0, but these vector are different from because, well, they're represented in a different way. Okay, so why this is all important to us? It's important to us because of the following reason. We are interested in fermions, and let's see what is going to happen if we go from one vacuum to another. So I will explain what do I mean by going from one vacuum to another. So let's solve the following problem. We have fermions in our theory, and so we can look at fermionic energy levels in different background fields. Okay. So we have Hamiltonian for fermions, which is nothing but psi bar, say d1 left, psi left, and h is equal to plus psi right bar. Here we have I dr1 psi r. So 1 is the Lorentz index here. Okay, so this is Dirac Hamiltonian for our theory. And what I will be doing, I will be finding the energy levels of our Hamiltonian. So let's first take one field is equal to 0. Then this is a trivial problem. We have a free field theory, and we can find all these energy levels. And the energy levels, so this is momentum k, this is E, they will be like this. And k is simply equal to 2 pi some integer number divided by L. We have discrete energy levels. Why so? Because we have compact space. Okay. So our system is living on the circle box. So this is the set of energy level for left fermions, and we have the same set of energy levels for the right fermions. Okay, so and you know very well interpretation of what is happening here. We have positive energy levels. Positive energy levels correspond to particles. Then we have negative energy levels. Negative energy levels correspond to antiparticles. And the way this is derived is that you organize a Dirac vacuum. And Dirac vacuum means that you fill all the negative energy level by particles. And then if you take away the particle with negative energy here, you're getting a hole. And hole has a positive mass, but opposite electric charge. Okay? So now, let's do the following. Let's gradually change the value of our gauge field. Okay, so I want to change A1 from 0 to 2 pi some integer number divided by L. Okay. And now some interesting things are going to happen. Because remember, in covariant derivative for left fields, we have the gauge field which comes with a minus sign. And here, in the right derivative, we have the gauge field which comes with a plus sign. Okay, and so when you change the the gauge field here, you pick up some level, then this level will go down because we increase the gauge fields. And if you look at right-handed fields, then this guy goes with the sign of plus, and therefore the levels will start to move in this direction. Okay? So what does it mean? This means that if you go from this vacuum to that vacuum, you will gain fermion number. There are particles appearing here, and there are So here, the particles will be disappearing. Okay? And here, when we move in this direction, the particles will appear. So the total fermion number of the system is going to change. And the change of the fermion number here will be equal to so E over 2 pi times L, the change of A1, and this is going to happen for left particle and right particle, but in opposite direction. So there is factor 2 here, and we will get here exactly the factor equal to 2m, and m is the number of windings which the gauge field made. Yes?
How did you relate the change of in spectrum to change of fermion number? I think I didn't get it.
Yeah, I just count the number of fermions. So suppose I say I start from a configuration which is a vacuum configuration. Okay, so what vacuum configuration means? Vacuum configuration means that all negative energy levels are occupied here and here. Okay, now we apply our gauge field, and let's see what is going to happen. Suppose that I go from configuration with 0 topological number initially, and finally I get the topological number which is equal to 1. So this picture will be changing to the following. So we move here by 1 minute, and so this level will be filled in But this guy will be empty because we started from a vacuum configuration. Okay? So what happens here? So this was the situation for left particle, and now situation for right particle. We move in this direction, all these levels were filled in, and when we move here, we'll get a level which will be filled in as well. Okay? So this means that we got right antiparticle and left particle. And now I'm looking at the fermion number. One is left, one is right. So this we got left antiparticle and right particle.
So you lose one antiparticle and you gain one particle, no?
Yes.
So then you get two more particles than in the beginning.
I'm trying to see now whether I put all the signs in the correct way. Particle. Electroweak theory. Sorry?
Two right particles are generated because left antiparticle is somehow
Yes.
right particle.
Yeah.
So you have two right particles generated.
Yeah. Not fermion number. Just 1 second. I maybe messed up the signs of. No, I think everything must be right.
What did you expect to get?
No. What you should get is that after this. I was. It's true that the charges are different, but then there is this gamma 5 stuff which distinguishes left-handed particles and right-handed particles. And what is actually happening, so what I made it wrong, is that so it was fine that the signs of EA are the same, but the movement of energy levels is in fact different. So everything goes up, okay? And this can be seen when you account for the fact that there is gamma 5 standing in these derivatives. Okay, so what basically happens is that these levels are moving up and these levels are moving up. So when we go from the configuration with zero topological charge to configuration with non-zero topological charge, what we are seeing that there is left fermion which is created and right fermion which is created. Okay, and note that since left fermion and right fermion they have opposite charges, there is no creation of any electric charge here. So electric charge is conserved, and there was a question yesterday whether this theory is anomaly free. So the answer, yes, this theory is anomaly free, and this process which we considered doesn't lead to creation of any net electric charge, exactly because the electric charges of left and right particles are opposite to each other. Okay, so this is kind of very non-trivial picture. Why it's non-trivial? Because it also plays with infinities, because the Dirac vacuum is a state in which all negative energy levels are filled, and when you move in this direction, what you are doing, that you are creating particle out of nothing, so to say. Okay, you started with a vacuum state, all negative energy levels are filled. You make this process, and you find that there is a production of net fermion number. Okay, and that we see really at the classical level, in the sense that we take the gauge field, we change it in some way, and we follow evolution of energy levels of Dirac operator. There is another way to see the same, and this way is based on anomaly equation. Okay, so what is anomaly equation? You can form the fermionic current, which is psi left gamma mu, psi left plus psi right gamma mu psi right. You would expect that this current is exactly conserved, so that d mu g mu is equal to 0, but you can compute the corrections to this equality, accounting for loop corrections. Okay, so what would be the diagram which you have to look at? So there is a dot which corresponds to the current, there is fermion loop, and then there is again the gauge part. Okay, and here the point is that if you regularize the current in such a way that it is gauge invariant. Okay, here, as you know, there is a subtlety in quantum field theory. So these fields are taken at the same point, and since they are taken at the same point, there are divergences associated with that. So you have to regularize this current. You have to do that in such a way that the product is gauge invariant. And once you account for that and compute the divergence of this current, you find that it's actually not equal to 0, but it's equal to E over 2 pi epsilon mu f mu times 2, and this is the famous anomaly equation. Okay, so derivative of fermionic current is not equal to 0, but equal to the dual of the field frame. And now you can do the following exercise. You can compute the change of fermionic current in this way, just looking at these pictures, looking at the way the different levels move, or you can compute the change of the fermionic current due to anomaly equation just by integrating it, and you will get exactly the same answer. Okay, so that's the integral 2 over 2 pi epsilon mu f mu d to x, computed for the time dependence in which you start from a1 equal to 0, and then you change to 2 pi m over L. You will see exactly that this number is integer, and this integer is equal to the number of energy levels which cross 0. Okay, so we can say that there is, in this theory, visibly there should be fermion number conservation, but in fact the fermion number is not conserved. Okay, once we have fermion number non-conservation, the natural question to ask is what is the rate of this process. And to understand what is the rate of this process, I will make a picture and then I will do some demonstration. Okay, so let's look at the plate where we have our complex field. This is a real part of phi, and this is imaginary part of phi. Okay, and then here is the potential u phi, and the potential is this type of figure, which you should rotate in this direction. Okay, and then we get here the set of the vacuum states. And so how do we visually see the different vector in this theory? So the trivial vacuum, which corresponds to, so phi is equal to exponential 2 pi I over L times integer number times V. Okay, so if we take n equal to 0, then our vacuum state is just a real number. It doesn't depend on x, and this is the point here. Now, if I take n equal to 1 here, and I forgot x, okay, then when our x goes around our spatial circle, the scalar field goes around this loop. Okay, and so this is the origin of the word topology. So what we have a mapping of our spatial sphere into the vacuum state. If you take n equal to, okay, there was n here. If you take n equal to 2, then what is happening? We go around once our spatial circle, and our scalar field goes twice around this loop. Okay, so the transition from the trivial vacuum, for instance, n equal to 0, and the vacuum with the topological number equal to 1, it can be basically represented as follows. So imagine that this part here is exactly this part of the potential. Okay, and then you have a vacuum state which is like that. And then in order to make non-trivial topology, what you do, you pull this loop and you put it on that. So then you can twist it, do it twice. I cannot do that with my watches. I can only do one topological transition. So what is important here? When you do this change, you see that the energy of your configuration changes because you have to climb the hill. So here the energy was equal to 0. Here the energy is equal to 0. But in the middle, there is some energy which is sitting in the scalar field. Okay, so this means that this transition, yes?
So is this only correct for symmetries that are spontaneously broken?
Yes, yes, yes. And the case when it's not broken, then there is no potential barrier.
Right.
Okay, and that is important thing for computing different probabilities. Okay, so what is the message here? When we are in the Higgs phase, and here we are in the Higgs phase, if we want to go from one vacuum state to another vacuum state, if we want to non-conserve fermion number, we should go through a configuration which has non-zero energy. Okay, and this we can represent to some kind of symbolically in the following way. Okay, so here I put in my field A, or it's better to say topological number. The energy of our system when topological number is equal to 0 is equal to 0. When it's equal to 1, it's again equal to 0. When it's 2, it's again equal to 0. And then there is some barrier between these two states. Okay, so this continues. And in order to go from here to here, we have to overcome the barrier. Okay. If we are in the vacuum, in classical physics, this is impossible. We don't have energy. The energy is equal to 0. We would stay here forever. If we are in the quantum theory, we can still do so, but this transition will be suppressed. And it will be suppressed by tunneling exponent, as we normally have in quantum physics. Okay, so in reality, of course, the picture is much more complicated. So why so? Because we are in field theory, and so the number of degrees of freedom is equal to infinity. And so you can imagine that here and everywhere there are infinite number of other directions perpendicular to the blackboard, for instance, which are changing this potential. And then there is some particular direction which is associated with a topological number where the structure of energy is periodic. Okay? So we go from here. And this is the process of tunneling. And the process of tunneling, it should be suppressed in some way. And indeed, you can do a computation and find out that there is a suppression of that. Yeah, and this is suppression happens to be associated with the vacuum expectation value of the Higgs field. Okay, so remember that in 1 + 1 dimension, the scalar field is dimensionless. So this is legitimate formula. Okay, so we have this theory. There are tunneling processes, and these tunneling processes are suppressed. Exactly the same happens in electroweak theory. I will talk about that later. But now let's ask ourselves what would be happening if we have this system at non-zero temperatures. Okay. And now, to understand what happens at the system at non-zero temperatures, I will make even more drastic step. Instead of considering field theory, I will consider 1 + 1 dimensional, just one dimensional quantum mechanics. Okay, and for this one-dimensional quantum mechanics, I will take a double well potential, ignoring the existence of infinite number of minima which we had in this gauge theory. So this is x, this is ux. So if you are here, you know how to compute the probability of going from here to here in quantum mechanics. No problem. It will, the probability will contain an exponent minus 2m ux integral dx, and you integrate between the turning point 8 and b, right? Now let's take the system and let's hit it. So when we hit the system, our system, not only the lowest energy level will be occupied, but also there will be excited levels here and there. Okay? And now, if you take an excited level, the probability of tunneling from the vicinity of this vacuum to this vacuum will go up. Okay? And eventually, for the levels which are above this point, this probability is equal to 1. Okay? So the system can freely evolve from the vicinity of vacuum to another vacuum. So,
But can
Yes.
So in quantum mechanics, if I remember correctly, the state is at the same time in both sides, no? So if I
You are talking about quantum mechanics. So the question was, what happens in quantum mechanics if we consider stationary state?
Yes.
And then your point is absolutely correct. If we take the double well potential and a stationary state situation, then there will be two types of level. So one type of level will be a mixture of this guy and this guy symmetric, and another type of level will be a mixture of this guy and this guy antisymmetric. And so the system is present simultaneously in both minima. So here the question is different. Imagine that we prepared initially a state which is not an eigenstate of Hamiltonian, but which is concentrated in one of the wells. So what is the probability for this state to go here? Okay, and then this probability appears. So here, when we increase the temperature, we say, okay, we take this left well, and we populate this left well in accordance with the Boltzmann statistics. Okay, and then there is some probability that we have a state here, etc., etc. And then what happens with the time evolution of this state? Okay, and then the levels which are below the barrier will tunnel, whereas the levels which are above the barrier, they can freely go into vicinity of another minimum. Okay, and then if the temperature sufficiently large, then the probability of going here from here will be just associated with the population of the energy levels around the barrier height. Okay, so if this guy is U0, then the probability will be given by exponential minus U0 divided by temperature. Okay, and we should expect to have exactly the same thing.
I'm sorry.
Yes.
I'm still struggling with this picture. So with the Mexican half potential, we can also go around the circle, not costing us any energy. We don't have to go above the barrier.
Mm-hmm.
But this seems to be a little. This one seems to be a two-dimensional thing that you're talking about. So I'm still not clear that I see the picture very well.
You didn't see the picture, perhaps because I didn't draw the picture yet. So the picture is the following. So this was a situation in quantum mechanics, right? And we were saying we put our system in the vicinity of this vacuum. Okay, then there is tunneling or there are transitions over the barrier. Okay. And here the point was that if we consider the system at 0 temperatures, then this probability will be exponentially suppressed like that. If you raise the temperature, this probability may be exponentially suppressed by this Boltzmann exponent. But if the temperature is very large, then there are no suppression whatsoever. Okay. So let's take this picture now and come back to our 1 + 1 dimensional theory. So now we have to use our imagination in a more, so how should I plot this? In a somewhat more elaborated way. Okay, so what would be an analog of the state here? The analog of the state here would be the following. We have phi field, which is equal to V plus some small fluctuations. Okay, and our A field is 0 plus small fluctuations. Okay, and we can visualize that as this is field phi, this is potential field phi, that there are some fluctuations nearby this point. Okay? And then this configuration corresponds to some excitations around this vacuum in this quantum mechanical example. So now let's construct analog of this point. So the analog of this point is the following. Our scalar field winds around this point and have small fluctuations. Okay? And then the transition from here to here correspond to taking this configuration, which is wiggling like this, to that configuration, which is also wiggling like this.
I guess my question is like, why does it cost us energy to go around that circle? I mean,
no, it doesn't. To go around the circle, it doesn't cost any energy whatsoever. No.
Okay. So what is that barrier? What is that?
Yeah, this is the barrier. Our potential has the form phi square minus v square square. And what I'm plotting here is an interior of this potential when phi field is smaller than v square. Okay? It doesn't cost us energy to be in this vacuum or in that vacuum. And it doesn't cost us energy to be in a different topological vacuum. What does cost energy is the transition from one vacuum to another.
This is one-dimensional, so there's no way to go around it. So x here is one-dimensional.
Oh yeah, if it is one-dimensional, I can understand because then you have to go above the hill.
Yeah.
But if it is really a circle that you can go, then.
But you cannot go. I mean, this is the potential. There is one configuration which lies down here. Right. This is another configuration which lies down. So imagine that, okay, this is a rope and this is indeed the circle. So this stuff is around. So the configuration which doesn't wind around, it's configuration which is like this. Configuration which winds is configuration like that. They both have zero energies or very small energies. But to transform one to another, you have to climb the barrier. Okay, so in mathematical terms, so let me, instead of showing you different watches, let me give you an exact mathematical formulation, so maybe it will be more clear what we have. So let's make the following. Let's take phi, which is a function of some parameter tau, and a function of x. And let's require that phi has the following structure. When tau is equal to 0, phi is equal to v, and when tau is equal to 1, phi is equal to v exponential I pi x times v. Okay? And we also have a1, which is a function of tau and x, which is equal to 0 when tau is equal to 0, and which is equal to 2 pi n over L if tau is equal to 1. Okay? And when tau changes from 0 to 1, all the changes in phi field and in A field are continuous. Okay, so we say that this configuration, which I constructed here, which depends on x and the parameter tau, this configuration interpolates between two vacua. Okay? Now, let's compute the energy of this configuration. The energy of this configuration will be equal to 1/2 d 1 phi modulo square plus lambda phi square minus v square square. Okay? There is no contribution of the gauge field because there is no magnetic field in 1 + 1 dimensions.
It's x. It is x for 2 equal 1, no?
And there is there is no x here. No, everything is fine.
But there is x for the 5.
Yeah, there is x here, but there is no x there. Because when you do a gauge transformation, the gauge field, you differentiate this guy with respect to x. So what is written here is fine. But what I missed is E.
Maybe there is an n. That's what you meant. There is an n in the exponent.
And there is an n in the exponent. Yeah, thank you very much. Okay. And so what we do, we compute here the total energy of this configuration. Okay? And as a result, we will get energy as a function of this parameter tau. Okay? And the statement is that it will be like that. Okay? Why so? Why will we get some extremum here? Why it will be not like this?
Can you repeat the question?
Yeah, the question. So she was. The question was the following. She was asking why at all we get some potential barrier between these states. You see, it's impossible another way around. Why do we know? We take this guy, okay? We take this guy, and we ask ourselves why, when this guy is equal to 0, okay? And we can answer this is a sum of two positive terms, okay? So this term must be equal to 0, and this term must be equal to 0. From here, we conclude that the only possibility to have 0 here is to have modulo phi equal to v, and or we can write that phi is equal to E alpha x v, and A is equal to a pure gauge. If this is not the case, then the energy of the configuration is greater than 0 because this is a sum of two positive terms. Okay. Now, can you go from this state to that state, or from this state to that state, being always in this situation? The answer is no. Why not? Because the mapping, this first state corresponds to trivial mapping. So you have your special circle, and you map it to the point. And this configuration corresponds to a non-trivial mapping. You have a circle, and you map it to the circle. So these are two different topological transformations. And you cannot transform one into another in a continuous way. And if you cannot transform one to another in a continuous way, then this means that you are going out of this class of configuration, and this means that there is a potential barrier between the two. Okay. So that's the proof of that.
But
Yes?
the energy of them is 0. No?
Sorry?
The energy of both of them is 0.
Energy of this configuration is 0, energy of that configuration of 0, and this corresponds to this point, to that point, but what is in between? and this is a function of tau, this is energy, what is in between is not equal to 0. There is absolutely no way to go from one place to another in such a way that you are in the gauge sector of the theory. Okay. Yes?
But does it just depend on the path that you choose to deform?
Whatever path you choose, you will, that was a very good question. You can choose one path in which it will be like this. You can choose another path in which it will be like that.
So the point is just this maximum. That's sort of
Yeah, so in order to make a sensible statement, a sensible statement could be what is the minimal barrier you have to overcome. Okay? And to answer the question, what is the minimal barrier you have to overcome, you apply the procedure which is called mini-max procedure. So what is this mini-max procedure? You consider h, this energy, which is a function of tau, of this parameter tau, and which is also the function of the path. Okay? So now what you do the following. You pick up a particular path, and within this particular path, you find the barrier height. You take another path, you find the barrier height. And then you minimize the barrier height with respect to the path. Okay, and that will give you some number here. Okay, so this number cannot be 0 according to this this construction. So just some number. Okay. And we will see what this number is.
Maybe there's some confusion over this Mexican hat. The Mexican hat assumes that phi is homogeneous, that there's no x dependence. But here there's x dependence. But this picture doesn't describe all configuration states.
Yeah, that's also a correct point. So well, Mexican hat, well, it doesn't tell that phi is homogeneous. Okay, this formula is valid for any x, right? But so what did you want to say?
That you can't, a single point in the space, the y space, doesn't describe all your field configuration.
Yeah. That's certainly true. Yeah. So in particular, there is also the term which comes from derivative of the fields phi.
But so this seems to rely a lot on the fact that space is compact. So that if you do one of these transformations, you have to wind your space in the field space.
Yeah.
But then, if space is not compact,
well, you consider the non-compact space as a limit of this one.
but for example, if I take there the
L to infinity, it will all stay the same. Yeah, and actually, we will see in a second that the configuration which corresponds to this point, it actually it survives when L goes to infinity. So this is a very specific configuration. Okay. Okay, so what I'm going to do now So let's see what would be an analog of the top of the barrier in our 1+1 dimensional theory. So we will see that this is a very specific configuration which depends on space coordinate and which is local in the sense that the energy of this configuration is finite. So this configuration is called Scalar, and it was introduced first in Electroweak Theory by Klintheimer and Manton, who found it in the standard model. So here the situation is a little bit simpler. We are in 1+1 dimensional theory. Okay, so in very general terms, I described to you this minimax procedure. Okay, so what we are doing, we are going from this vacuum to that vacuum by many, many different paths. And we are trying to find a situation in which this barrier is minimal. So once you are talking about some minimal in field theory, then this minimal should obey equations of motion. Okay? But the configuration which corresponds to the sphaleron, to the top of the barrier, it should be a solution to the equation of motion which has one negative mode. Okay, so let me explain you what that means. Let's go back to quantum mechanics, where we have this type of potential. And here, the top of the barrier was corresponding to this point. Okay, and this point is a solution to equations of motion in this 1+1 dimensional theory. Right? The equations of motion look like x double dot is equal to minus du over dx. So this point, x equal to 0, is a solution to this equation, right? Because first derivative of the potential here is equal to 0, and this is time-independent configuration. However, this point has a negative mode. What does it mean? This means that if we make a displacement from this point, the energy of the system will decrease. Okay, and that's why this point corresponds to the height of the barrier. So here we are in an infinitely dimensional space of field theory. And we want to find a path which is the best one. And then this path, it's like this in one direction and like that in orthogonal direction. So two-dimensional picture, which you can imagine. Okay, if you go to the mountains, there are these saddle points which you can see. Okay, so we have infinite number of dimensions. So we have infinity of this type of behavior and only one like that. And then this is indeed the top of the barrier. Okay, visualize that very, very easily. If you go to the mountains, you want to save your energy, you go through this type of points. Okay, and this corresponds to the height of the barrier. You cannot do better than that. Okay. So what we should look at in our theory, we should look for solution of equations of motion with this property that there is just one negative mode. Okay. what is our theory? Our theory is a scalar field plus the gauge field. Okay, gauge field in 1 + 1 dimensionals is basically non-dynamical. And so the equation which we have to solve is just a scalar field equation. Box phi is equal to minus du over d phi. And this is a equation for the scalar field. And if I take a particular direction in phi, for instance, take phi real, we have double wall potential, and I guess you know very well that there is a solution to this equation, which is non-trivial, which has different asymptotics when x goes to plus infinity and minus infinity, and the solution is called kink. Okay, and this solution it looks like the following: phi x is equal to hyperbolic tangent of mhx over 2. This is the mass of the Higgs field here, and so this is the function. And so what happens with the field phi? It just changes like this.
So this is in 1 + 1.
This is in 1 + 1. Yeah. And this solution, it has finite energy. It's localized solution. This is phi. And if you plot, say, the energy of this solution, then it looks like this, energy density. And this scale here is 1 over mh.
So is this a solution?
No. In this theory, no. In phi to the 4 theory with a real scalar field, yes.
And what's the difference?
Sorry?
What's the difference?
Well, the difference, and that's the difference is a very important point. If you have phi to the 4 theory with a real scalar field, then this type of solution is stable. If you look at small fluctuations around that solution, you will find that they all have positive frequencies. And if you take this solution with small fluctuations around it, it will stay forever. Okay. Here, this cannot be the case. And you realize that immediately. So why so? We have not a real field, but we have a complex field. Right? And now if I plot again our double well potential, but now this is a Mexican hat potential. Our solution here, it stays here at 1 infinity, and then it comes to this infinity, and then it goes like that. It's always positive. Now you see that this solution here, it cannot be stable. You take this part and you pull it down. You cannot do that if you have just the real scalar field, because there are no other directions. But here we have a complex field, and we move it in the direction of complex field, and we immediately decrease the energy. Okay? So, and this solution has chances to be our spheroid. Okay? And let me modify this solution. Yes? Sorry, there is no time dependence. And spheroid is the configuration which is time independent, which corresponds indeed to the top of the barrier. When you climb the mountain, your trajectory is time dependent, but you arrive to the top you stay there, you relax for some time. So this is time-independent configuration. Okay, so let me modify a little bit this configuration in the following way. So when we were talking about this transitions, right, we had in mind the following picture, that we start from this configuration, which on this picture is represented as a dot. And we finish with configuration, which is on this picture is represented as a circle. And the can I have another color? Okay, I'll take this one. When we arrive to the top, it should be something like that. We go here to this point, and then we come there. So that's, and this is indeed, we take this circle, we make it larger, we come to the configuration which corresponds to the top, and then we pull it down. Okay, so our Scalar configuration, it should correspond to that. And we can take this one and just multiply it by the different factors to look at like this with the use of the gauge freedom which we have in our theories. So Scalar, we can write it as follows. It's V I hyperbolic tangent mh x over 2 exponential I pi x over L, and A1 is equal to 2 pi over L times 1/2. Okay, A1 was equal to 0 initially, and finally it was 2 pi n over L. So I'm taking n equal to 1. And now we are halfway, so that the gauge field should be equal to the half of its value in another value. Okay, and so I'm taking this guy here, and what I wrote is nothing but a gauge transform configuration which put everything in the correct boundary conditions. Okay, so this guy here is a solution to classical equations of motion. You can check this required a computation that this is a good solution in the sense that it has exactly one negative mode. Okay, and so it indeed represents this point, very specific point in the this multidimensional space, infinite space, which corresponds to the top of the barrier you have to overcome. Okay, now you can ask yourself, what is the height of this barrier? How to answer this question? Okay, very easily. You have configuration, you insert it into energy, which you have, and which I erased. You do a computation, and you get the answer. Okay, and the answer is the height of the barrier E Scalar is equal to lambda v to the 4th mass of the Higgs field. Yes?
Obtain the configuration that you mentioned, should we do the minimax procedure again to obtain?
Yeah. So the result of minimax procedure must be a solution to equations of motion, but with one negative mode. Okay, and whether this solution is indeed a global minimum, this is somewhat more subtle question. Okay, so that it's indeed represents a good path, you can check in a local way, computing deviations from this solution. And if you find that there is exactly one negative mode, then you say that, okay, this is fine, this is a good solution locally. It might exist some other solutions which are even better than this one. So this is not excluded because this is a multi-dimensional point, and you can have, so imagine that you have, I'm writing a direction which is orthogonal to this topological direction. So imagine that you have something like that, okay? So you found, for instance, this point. You can go the mountain in this path, or you can go the mountain on this path. You can go the mountain of this path. So this path will be better than this one, okay? And to find which one is the best, you have to do the global analysis. So here it's known for this theory that the picture is just like this. Okay, so there is just one path you can go, but this is a question which is non-trivial, and you should do some numerics in order to convince yourself that indeed you have just one spheroid. And we know examples in electroweak theory where this is not the case. Okay, and particularly if the Higgs mass is large, there are several spheroids of this type, and only one of them is the best.
How do you see that this has one mirror mode, like precisely one?
That it has.
See this or is it more?
No, then you have to do a computation.
All right, okay.
This is a straightforward computation, so it's the computation which you can do around any type of classical solution. So what you do, you take the action of your system, you put there your classical solution plus small fluctuations, linearize, make quadratic, look at second order differential equation for perturbations. This is normally represented. No, it's not obvious. Okay, it's obvious that this solution is unstable. Yeah, from this picture, because this is a complex field, and you just visualize the way you decrease the energy. So this is obvious. Whether it's just one direction of u is a result of computation. And well, as I said in electroweak theory, if you find a solution, a similar type of solution for large Higgs masses, it happens to have two negative modes instead of one, which signifies that there are other solutions which have just one negative mode. Okay, but you can't do that without a computation. Yes.
Maybe I have some confusion now on my mind, just to clarify. So, I mean, this is a solution of the equation of motion. So basically, this is a scalar field solution. So this spheronic solution is not the gauge transformation that maps this.
Okay, so what I was doing is the following. Okay, I take scalar field equations, put gauge field to 0, just solve that. Okay, and then we are getting this hyperbolic tangent.
Yeah.
Well, actually in any direction. But then I say, okay, actually I'm interested in spheron, and I'm interested in the situation when I do have the gauge fields. Okay, and then I have to modify my solution. Why so? Because for spheron picture, I was insisting that my initial state corresponds to just the field where the scalar field is equal to some value. This is not true for my solution, right? Because at 1 infinity it comes to this vacuum. In another infinity, it comes to that vacuum. But now I do a gauge transformation, and I can do so. I put in this point to this point. And then I find out a configuration which still satisfies equations of motion, but it also satisfies the boundary conditions we require for this folder.
So that configuration is a gauge configuration.
Yeah, it's a gauge configuration. It's still a solution it's still a solution of all equations of motion, but now with the gauge field included, because this is a gauge theory and because we made the gauge configuration. However, the point is that it does satisfy the boundary condition I want to impose on this configuration.
Yes.
Okay. Yes?
So in the uppermost line, what do you mean by this I after the V?
This is just imaginary I. Okay, so it's just a solution constructed in such a way that when you see, if I take x equal to 0, then no, yeah, thank you very much for asking this question. I was not particularly accurate here, I guess. Yeah. So x here is changing from L over 2 to L over 2. I changed the beginning of coordinates, so sorry about that. So now
You want to depict the red line with that solution?
yes. Yeah, so this point is correspond to x equal to 0. So I want to put the center of Scalaron at x equal to 0. And now you see what happens if x is equal to L over 2, then this factor is equal to plus I, and when x is equal to minus L over 2, this factor is equal to minus I, but also hyperbolic tangent, it changed the sign, and so that we are getting one and the same value at x equal to minus L over 2 and x equal to plus L over 2. So it exists indeed correspond to this point. Okay, sorry, I changed the notations on this point. So, more questions?
Are there instanton solutions?
Sorry?
Are there instanton
Yes, there are instanton solutions in this theory, and the instanton solutions in this theory is just Nielsen, Olesen, Abrikosov string, and this is completely different type of solution. So the question was, are there solitons here? The answer is yes. There are instantons. So, and this instanton corresponds to the following. You go to Euclidean version of this theory, and then you find a solution which would correspond to a strain in a superconductor. Okay. And this solution, they are important. So these solutions are fixing the tunneling exponent when we are dealing with fermion number conservation at 0 temperatures. Yes?
But the instantonic configuration as kind of the does they have kind of the same meaning?
No.
Because from the topological point of view, they also, if I remember correctly, represent some configuration that are able to map one vacuum to another one.
Yeah. So Okay. So if you can ask the following question. So here, when I was talking about transition from one configuration to another, I considered this parameter tau just an external parameter, and I was talking about the energy of the system. So the instantons, they correspond to a different idea, but extremely close to that. You take a Euclidean theory, then this parameter tau is not a fictive parameter, but it's imaginary time. And then you are searching for solutions of two-dimensional Euclidean equations of motion. And then you can fix a particular gauge in which when this true Euclidean time goes to -infinity, you are coming to this configuration. And when your Euclidean time goes to +infinity, you are coming to another configuration. So instanton is this type of process. It's non-static. It's occurring in Euclidean space-time in which you are doing the same as here. Yeah. So they are related to each other, but you cannot derive Sphaleron solution from the instanton one and vice versa. And also the level crossing phenomena, which I was talking to you about, is also closely related to different instanton transitions. So you can prove the following theorem. If you have a level crossing like this, then there are zero modes for fermions when you consider instanton solutions. So this is a famous index theorem which shows the relationship between these two phenomena. Okay.
So in this sense, it is wrong to say that this Sphaleron and the instantonic solution are related to each other in the changing from the Euclidean space over the let's call Minkowski space.
Yeah, kind of. Yeah.
So is that because that's static and instanton is dynamic?
Instanton is dynamic, but in Euclidean space-time, and this guy is static. Yeah, but yes, they are related to each other. For instance, okay, you take Electroweak theory, just as it is. The Electroweak theory doesn't have precise instantons, in the sense that there are no Euclidean configurations which go from one vector to another. There are some approximate configurations, but there is exact Sphaleron configuration. So there is a relationship, but this relationship is the existence of one doesn't necessarily imply the existence of another.
And what's an instant?
Or, yeah, sorry?
Instanton is a... What's an instanton?
Instanton is a classical, is a solution of classical Euclidean equations of motion.
So it's the same as soliton.
It's not soliton. Soliton is a solution to Minkowskian equations of motion. So these are things of really different nature. Solitons are a solution to Minkowskian equations of motion, and solitons are the solution which don't have any negative modes. So the soliton solution, in a sense, they are behaving like particles. Okay, so the kink I was talking about in two-dimensional theory is just a lump of energy which can move left, right, whatever with whatever velocity. It looks like a particle. Okay. So instantons are solutions which are associated with another physical phenomena, which is tunneling. So for instance, if you have a double well potential, then there are transitions from one to another, and this again can be described by instanton. You take this quantum mechanics, go to Euclidean space, and again you find some solution which corresponds to that. And Sphaleron is yet another solution which corresponds to the top of the barrier. So there are different types of solutions. They have different physical meaning. There is a relationship, physical relationship of instanton to Sphalerons and vice versa. Yes?
So in this one-dimensional model, these winding configurations, they don't have a fixed core or a magnetic core, right?
No, they don't, because there is no magnetic field in 1 + 1 dimensions.
Yeah. So how to think about them when you say they correspond to these Nielsen-Allison vortex?
Ah, okay, but then this is instanton. Instanton, you still have dynamical field F01. Okay, so the situation is the following. So this theory is good also for superconductivity. Okay, so let's consider this theory in 2 + 1 dimensions. Okay, so you imagine that there is a plane and then there is a time. Okay, and then you take this theory and then you can find the Nielsen-Olesen string. And in this Nielsen-Olesen string, the component F12 corresponds to magnetic field. Okay, and in Euclidean space, this solution gives you exactly the instanton, and you can interpret that as magnetic field. But here, for us, here we have 0, 1 component, so we have electric field, but no magnetic field. If you go to Euclidean, you can think about that as magnetic field. Okay, I actually didn't go to what I was intended to go, and actually my time is up. So I just...
Is this a reasonable point to stop?
Okay, so let me just conclude. Okay, so what this discussion is telling us. So we have 1 + 1 dimensional theory. In this 1 + 1 dimensional theory, at first sight, fermion number is conserved. But if you look at the problem more closely, we see that in fact it's not conserved. Okay, and we saw that by 2 different ways. One, by analyzing what happens with fermionic energy levels when we change the gauge field, and another way we didn't go through in deep detail, but there is anomaly in fermionic current in this theory, which leads to the same effect. Okay, so that's the statement number 1. Fermion number is not conserved. Second statement. We got an insight what is the dynamics in this theory and how to estimate, compute, to get understanding of the rate of this non-conservation. And for this end, we considered the transitions between the states with different topological number, and we saw that there is some barrier to overcome. Okay? To overcome this barrier is suppressed by E minus some number, tunneling exponent. So this process is highly suppressed at 0 temperatures. However, at large temperatures, the suppression goes like E Sveleron over T, and this suppression can literally disappear if the temperature of the system is very large. Okay, so in this toy model, we got a very interesting physics from the point of view of baryogenesis. And this physics is that at ordinary conditions, small temperatures, the probability of fermion number non-conservation is very small. We want it to be small because we don't observe it. At very high temperatures, the rate can be large, and that's exactly what we would like to have for baryogenesis. Okay, so this is the summary of physics which we considered so far. And, well, basically, the lecture this evening, I will draw the analogy with Electroweak theory. I will not go in detail in Electroweak theory, but I will show you what are the analogy, and this analogy will happen to be pretty precise. Okay, so I'll stop here. Yes.
Could you please again elaborate a little bit on the difference between the fermion number and the charge, because you were saying that nevertheless charge is conserved.
Yeah. Yes. Okay. Yeah, indeed. Sorry, I wasted some more time on this point because I was confused. So the Lagrangian which we considered, it has the form dl psi l, and here we have psi right, d right, psi right. Okay. Depending on dl and dr, there could be different variants of this theory. So the choice which corresponds to electrodynamics is the following. dl is equal to dr is equal to d minus ea. Okay, so if we have this charge assignment, the left-handed particle and right-handed particle have the same charges as its normal electrodynamics. Okay, and then this theory is anomaly free. Okay, there are no gauge anomalies whatsoever. However, in this theory, there is what is called chiral anomaly. So if you have a current like that, psi left bar gamma mu psi left minus psi right bar gamma mu psi right, this is g mu 5, then this current is anomalous, and the derivative of this current, d mu g mu 5, is equal to epsilon mu f mu. Okay, and you have exactly the same as in normal electrodynamics. I wanted to discuss here the non-conservation of fermion number, and therefore I changed the charge assignment. I used for left the sign plus here, and for right the sign is the sign minus. Okay, and this changes the situation so that the fermion number is not conserved, but still the theory doesn't have anomaly. Okay, and the way to see that, so I was talking about level crossing where we saw that, but you can see the same if you compute the divergence of this current. So to compute divergence of this current, you basically have this type of graph. So this is left field, and then here you have this current, and here you have right field and right field. And these loops, left loop and right loop, they come with the opposite sign. Okay, so when you compute, so let's take the theory with the assignment which I used, plus and minus. Okay, then electric current, it is given by this formula. If I use this charge assignment, and then you have here the following. So for left, you have plus sign of this vertex. For right, you have minus sign on this vertex. But here you have again plus sign. Here you have again minus sign. And this loop comes with a minus sign, so you get a consolation between this contribution, and so this theory is anomaly free, so it doesn't have anomaly in the gauge current. Now, when you compute anomaly in fermionic current, then in fermionic current we have plus sign here, and so we have plus sign there. And when you sum these diagrams, you see that there is non-conservation of fermionic number. But I could have done everything with the chiral charges. I just prefer to do it with fermion number because then it has a closer analogy with electroweak theory. Okay. you.